Hello mathematicians, we're now going to look at vector projections. And in vector projections, what we're concerned with is how much of one vector points in the direction of another one. So the projection of one vector onto another, in terms of geometrical appearance, involves dropping perpendiculars from the ends of one vector onto the one upon which it's to be projected. So that what we're doing is equivalent to, in physics, finding the component of u in the direction of v, the component of one vector in the direction of another. So if we had u and v set up as here, then the projection of u onto v, which we write as the projection with the sub v and u, so obviously u is on v, is a way of remembering this, is shown in blue. So in other words, we take our vector u, we drop the perpendicular down, and what we're doing is finding the component of u in the direction of v. And we just work with simple trigonometry, as we'll see later on. If we project v onto u, then by the same process we get the little red vector here, which is written as the projection of v onto u, and that's shown in red. So let's just consider one of these, the projection of v onto u. So here's our vector v. So the red vector here formed when we drop the perpendicular down is the projection of u onto v. Sorry, v onto u. And from trig, the magnitude of this vector here that we're after is simply given by the fact that the length of that line there is equal to v cos theta. So we need our magnitude signs in here. So the magnitude of the projected vector is equal to the magnitude of vector v multiplied by cos of theta, the angle between the two vectors. Now, you might remember, again for the physicists, and it's no big deal if you're not, but this is exactly how we find the component of a vector v at an angle theta to itself. It's v cos theta, which is what we've got here. Now, if we just do a little bit of algebraic manipulation, if we multiply top and bottom by the magnitude of u, you can see that what we've got up the top is the dot product of vector u times vector v. So we can say that the magnitude of the projection of vector v onto u is the dot product of u and v divided by the magnitude of u. But that's still only giving us the magnitude of the projected vector. So if we take that idea a little bit further still, then the direction of the unit vector, that should say u, that should say the direction of the projection of v on u is given by the unit vector in the same direction as u, which is this. So our unit vector is the vector u divided by the magnitude of the vector u. So if we come back to our expression up here for the magnitude of the projected vector, then we add in the direction. It has a magnitude u dot v on the magnitude of u, and it's in the direction of vector u divided by the magnitude of u. So what we've got is that in vector form, the projection of v onto u is u dot v on u squared by u. Now, if we look at this example in particular, we can see by observation that u is 3i plus 3j, takes us up to there. So these are our position vectors. V is 4i minus 3j, and we want the expression for the vector, which is the projection of v on u. So if we work out little bits and pieces, we can see that u dot v is, if we use our this form of the dot product, scalar dot product, where we multiply the x components and to that we add the product of the y components, you can see that u dot v is, as we expect, a scalar whose value is 3. The vector, which is the projection of v onto u, in other words this, is the projection of v onto u equals u dot v on the magnitude of u squared times u. So u dot v we've just worked out is 3. Magnitude of u squared is the x squared plus the y squared, and because it's squared, there's no square root. And we multiply that by the vector u, which is 3, 3, if we write it in column vector form. So that's 1/6, so all of this resolves to 1/6 of 3, 3. And we can decide for ourselves whether we take the constant inside and write this as 0.5, 0.5, or we can write it in Cartesian form as 0.5 or component form, 0.5i plus 0.5j. Now, when we do projection, there are a couple of little rules to help us with the arithmetic. So the projection of lambda v onto u is lambda times the projection of u onto v. And I think if you don't get bamboozled by the terminology, that makes absolute sense. The projection of v plus w onto u is the projection of v onto u plus the projection of w onto u. And one more little piece of interest is if we try to reconcile our physics interpretation with the maths interpretation, and again, if you don't do physics, that's no big deal. But for the physicists, if we think about the dot product of two vectors as the magnitude of one times the magnitude of the projection of the second onto the first, then the way that we deal with that in physics is that we would say, for example, work, which is a scalar quantity, is, well, we don't refer to it in physics as F dot S, but that's what it is. We would say in physics that it's the component of the force vector in the direction of the displacement vector. So the component of the force vector in the direction of the displacement vector is the magnitude of F times cos theta, and we multiply that by the magnitude of S. So that's exactly what the formal mathematical definition says, because we can take the constant into the expression as shown on the previous page. So if we look at this previous example using a physics mindset, we can say that u dot v is the component of v in the direction of u, and given that that angle there is 81.87, which we saw in a previous video, that means u dot v is 5 cos 81.87 times 3 root 2, which is 3, as we again saw in a previous video. And it also corresponds to the value that we got using the product of x components plus y components.